Now if we turn to page 548 to number 21, it's part of our Unit 6 review. We're going to try to avoid kind of the question. We're going to try to look at the idea of a Hess law example to find the delta RH of the question. Now, all I did was write out the reactants and the products and the reaction of number 21. And it talks about the it's the burning of sulfur or the extraction of it. And so all we're going to do is try to find a Hess law so that we can do an EP graph at the end with an activated complex. So, we're going to do a Hess law shortcut, and all we're going to have to do is, like any Hess law question, we're going to find a delta RH by finding the N times delta RHM, the moles per molar enthalpy of products, and the sum of it, so that just means sum, it's kind of like a Greek letter, minus the sum of the moles per delta RHM of reactants. And so that's all we do. So we're going to take a delta RH and try to figure out our molar enthalpies of it. So all we're going to do is turn to page 4 and 5 of our data books and find out these formation enthalpies. So we're going to first look at our products and realize that it's H2O gas. And it's important to realize if it's H2O gas or H2O liquid. And we know we got 16 moles of this times water vapor, so negative 241.8 kilojoules per mole. And that's what every delta FHM is for all of our formation reactions. And sorry, I just boxed it off, but we know that sulfur by itself has 0 kilojoules per mole because it's just an element. So we can just skip that step. And now we're going to subtract it by the reactants. So we got 16 moles of hydrogen sulfide, so H2S. So we're just going to try to find that, and we find hydrogen sulfide here, negative 20.6, that's on page 4. So 16 moles times negative 20.6 kilojoules per mole plus, so that's the sum of 8 times sulfur dioxide. So we're going to find that sulfur dioxide. Sulfur dioxide, SO2, negative 296.8. So 8 moles times negative 296.8 kilojoules per mole. So what we're going to do now is grab our calculator and start plugging in this to find out what our delta RH of the question is. So we're going to go in box 16 times negative 241.8 minus in brackets 16 times negative 20.6 plus 8 times negative 296.8. And that all equals negative 1164.8 kilojoules. The moles will cancel, leaving us with kilojoules. And so, just as a reminder of our 4 ways of communicating it, so our first one would be our delta RHM, or our delta RH. So this would be 1. Our next way would be saying that 16 H2S solid plus 8 SO2 gas forms H2O gas plus 3 S8 solid. And then off to the side, you do delta RHM is equal to negative 1164.8 kilojoules. Our other way is to also write it as a product, and to kind of not to write it out again. All you do is bring it on the product side and add 1164.8 kilojoules. Our last idea would be to draw an EP diagram, and that's what we're going to do here. But we're going to draw it with the idea of this activated complex, okay? So we're going to draw this EP diagram. So EP in kilojoules and reaction process increasing. We just call this reaction of 16 H2S solid plus 8 SO2 gas. And we know this is an exothermic reaction because of this negative sign. So our reactants are going to be 16 H2S solid plus 8 SO2 gas. Go to peak. So this hit their activated complex, and then slowly, or actually quickly, very quickly, most reactions take about a second or less to occur, and we have our products forming. That'd be 16 H2O gas plus 3 S8 solid. So we'll just label this an activated complex. We'll have our delta H, delta RH lower than our reactants. So our products are lower than reactions, showing our exothermic reaction. And we're going to label this difference to be 1,164.8 kilojoules. That'd be from here to here. Not really drawn to scale, but just kind of your idea. And we know, to label it completely, that the difference between our activated complex, the difference between our activated complex and our reactants is called our activation energy, which is also kind of known as our bond energy. Kind of, not really, that'd be of a chemical in their ability to, so if it was just one compound and it was decomposing, that would be the idea of a bond energy. The amount of energy needed to break apart this puzzle piece or this compound would be our bond energy, also known as the activated energy inside that. So our activated energy is just the difference between our activated complex all the way to reactants. Now, a way to decrease this or to show this with a catalyst, so if the question were to ask you, show EP diagram with a catalyst. I'll draw that in a different pen or in pencil. So one of the most important things to remember about catalysts is that it does not affect either the products or the enthalpy change. So when we show our activated complex of a catalyst, it would just be lower and produce faster. So if we could draw it maybe steeper, I'm not the best drawer, but the whole idea is that it'd be slower and faster. So with catalyst, draw the activated complex lower and faster. So maybe it'd be kind of starting all the way over here. Or you kind of get the idea that the reaction would occur faster. Kind of going back to how to affect the reaction rate. So you'd have less energy and a faster reaction with the catalyst. And this is why a lot of industries use this for more effectiveness and less energy consumption, leading to higher products, and products as in money and wealth. So we're going to start the Unit 6 review, shown on page 547. And so we're just going to pick a few questions to do. This will combine Learning Guide 3 and Guide 4. Really similar. The only difference is one has catalyst and this still has So catalyst, bond energy, and activated complex. Where this one has Hess law and specific heat capacities and molar, both of them have molar enthalpy. This has heat transfer changes. Kind of more of the calculation, and this is more theory. So number 2, we're going to start with that. Says water on page 547. Water can be decomposed by electrical energy as shown in the following equation. 2H2O liquid forms 2 hydrogen gas, 2 moles of hydrogen gas, and 1 mole of oxygen gas. And so this is a decomposition of H2O liquid. And they're trying to ask us what is the value of delta RH. And it's a numerical response question measured in kilojoules in kJ. So really what they're asking us is to do a Hess law question, or if you already see how to quickly do it, is use your data sheet. However, if you just jump to your data sheet, you might get it wrong. But anyways, we'll jump to it. So H2O liquid is negative 285.8 right there kilojoules per mole. Now we need to realize that we have 2 moles of H2O liquid. So we're simply just going to times it by, so negative 285.8 times 2, which is equal to negative 571.6 kilojoules. And that would be our delta RH. However, that is not our delta RH of the entire question. And so with any Hess law question, we have to realize that the sum of our products, of our enthalpy of that, is equal to subtracted by the sum of our reactants. So products minus reactants. And we realize that our products are equal to 0 because they're just hydrogen and oxygen. So those are elements, minus a negative 571.6 kilojoules. So our delta RH of this question is actually positive, meaning endothermic is equal to 571.6 kilojoules. And in proper sig digs for our written response would be 572 kilojoules. And you're going to leave out the kilojoules since you'd just be writing it out. Now, we're going to go and explore number 4 and 5 on still page 547. So number 4 and 5. Starting with number 4, it says, which statements are true for exothermic reactions? So, what, if you can read this, kind of trying to allow you guys to follow along and me have the majority of the page. But which statements are true for exothermic reactions? Chemical bonds are broken. Now, I'm going to have number 5 here as well, also at the same time. And we know, and it is important to realize that in exothermic and endothermic, so number 5 reads, which statements are true about endothermic reactions? So this would be endo, and this would be exo. Chemical bonds are always broken, and either can be in exo or endo, so both of them get 1. Along with number 2, chemical bonds are formed in an exo or an endothermic reaction. Chemical bonds can be either broken or formed, and that's for each. It's kind of important to realize. However, 3 to 6 for options start to realize the difference between exo and endothermic reactions. So number 3 is energy is lost to the surroundings. Now, that idea will always lead you to exothermic. And that's because the whole idea of exothermic reaction is more energy is being released to the surroundings than absorbed to the compound. Whereas endothermic reactions is where energy is gained from the surroundings. So that's number 4. The chemical, number 5 says, the chemical potential energy of the products is less than the enthalpy of the reactants. The chemical potential energy of the products is less than the enthalpy of the reactants. So the products are less than the reactants. And so this is kind of leading towards our EP diagrams for each, or I can draw them, whatever. This would be, let's label it exo, and this is endo. Exo, we know, has always an activated complex and a reactants, but exothermic is where the products are less than the reactants. So that would tell us that number 5 is for exo. Where endo will have the reactants, also with an activated complex, however, has a positive enthalpy. This would be a negative enthalpy because it's less than the reactants. This is more, hopefully. I didn't show much of a difference, but hopefully you can see that. And endo is where number 6 states the chemical potential energy of the products is greater than the enthalpy of the reactants. So if the products have more energy than the reactants before the reaction, that is because they're absorbing some of the energy from the reaction, making it an endothermic reaction. If the products have less energy than the reactants after the reaction, we know this is an exothermic reaction. And this is because some of the energy is being released to the surroundings rather than absorbed to the reactants or the products. Number 6 says the energy, still on the same page, 547, the energy barrier that must be overcome in order for reaction to occur is referred to the activated energy, bond energy, enthalpy change, or molar enthalpy. And we know that in any reaction, our activated complex must always be overcome in order for reaction to occur. So that would be most definitely A. And how we can overcome the reaction easier is by our concentration or temperature or pressure. So write this down. Temperature as a reminder. Pressure. Concentration. And catalyst. Did I miss anything? Oh, and surface area. Perfect. Number 7 states, catalysts are an essential part of most industrial chemical processes. Which of the following statements about catalysts is false? Catalysts are not consumed in the net reaction. Maybe. Here, let's do an A, B, C, D. That sounds kind of correct. So let's just keep on going. Catalysts increase the enthalpy of our products. Now we know that catalysts have nothing to do with their enthalpy change. And that is important to realize. No matter what our activated energy, once we calculate our Hess's law or however we find it, our with the catalyst or without, our enthalpy is not changed. So we know B is completely wrong. Catalysts increase the overall rate of the reaction. Now, that's true. Oh, it's asking what is false. So we know B would be correct. Sorry. But anyways, C is true. A is true. Catalysts are not consumed in the net reaction. And that's the idea of the enthalpy change. When you do a net reaction, that is what are our reactants and what are our products. Our catalysts will never show inside either reactants or products in a net reaction. Catalysts provide an alternate pathway for the reaction, and that is also 100% true. Just like our puzzle pieces, it is allowing us to have more energy or allowed us to orientate, going back to that puzzle design on page 537. We know that it orientates our reactants so that our products can form that much easier without affecting our products. And kind of showing that puzzle, how much less energy would it be if you wouldn't have to worry about one of those, either the orientation or the energy or the amount of energy and collision. Number 8 says, using a catalyst in a chemical reaction pretty much the same question, increases the enthalpy change of the reaction. A, B, C, D. A is definitely wrong. Enthalpy does not change with the use of a catalyst. Increases the activated energy of the reaction. Now we know that the reason that we use a catalyst is to decrease the activated energy, so B would be wrong. C says catalysts increase the overall rate of the reaction. And reading a different question. C says decreases the enthalpy change of the reaction. We still know that enthalpy change does not get affected by a use of a catalyst, so C is also wrong. So D must be right, but let's read it. Maybe I'm wrong. Decreases the activated energy of the reaction. And we know that that's the whole idea of using a catalyst, that it decreases the amount of energy we need to form this reaction. Looking at number 9. Now, looking at number 9, a chemistry student determines that the molar enthalpy of combustion, so molar enthalpy of combustion of methanol is negative 721 kilojoules per mole. Now we know that methanol in a combustion is writing methanol plus oxygen to form a complete combustion, which is CO2 and H2O, which is shown on our number 9. Right? Where's number 9? Right here. And so, all it's saying is to write energy as a term inside a reaction if methanol is negative 721 kilojoules per mole. What would it be if we have 2 moles of methanol inside our question? So we have 2CH3OH liquid plus 3O2 gas to form 2CO2 gas plus 4H2O gas plus energy. And so what we would have to do is realize that our delta RHM of the question of methanol is negative 721 kilojoules flat. To find our delta RH, to write it as a product, because it's a negative, we would have to times, to find delta RH, we always have to find times our molar enthalpy by our moles of whatever our molar enthalpy is. So we'd have to times negative 721 by 2, which is equal to 1442. Negative, here, let me just double check that. Negative 721.2 times 2 is negative 1442. Oh, no, 0.2. Sorry about that, guys. Just negative 721 times 2, which is negative